In this video, we're going to introduce the idea of linear programming. And a linear programming problem asks us to take a region described by a set of linear inequalities, such as the one we see here, and then ask us a question about another function. For example, if I have this function, z equals x plus y, I might ask, what's the largest possible output I could get from this function if I'm only allowed to plug in points from the region where the points satisfy the set of inequalities? So, for example, the point 2, 2 is in this region. So I'm allowed to plug that point into this function, and I can get an output of z equals 4 at that position. There are other points I could plug in as well. 1, 1, 3, 1. So there are lots of points in this region, and different values would give me different outputs for z. Like if I plugged in 1, 1, my output for z there would be 2. So what if I want to know what's the largest output I could possibly get? In order to think about that, we're going to draw some lines. If you think about an output from this function, like the output 2, that corresponds to a value of z. And if you want to know what points you can plug into the function that might produce that output, all you have to do is ask, well, when does the formula for the function, the x plus y, when does that give me 2? And the set of points that satisfy that condition are the points on this line. So if I take any point from that line and plug it into this function, the output will be 2. And we notice that there are several points inside the green region that are also on this line, which means there are lots of points I can plug into this function that give me an output of 2, like the point 1, 1, or the point 2, 0. So I can definitely get an output of 2. I could also get an output of 4, because if I draw the line that corresponds to setting this formula equal to 4, I can plainly see that there are points in the green region that are on that line. And any of those points, if I plug them in to this formula, gives me an output of z equals 4. So I could do that with other lines as well. But eventually I'll see some lines, like this one, that don't touch the green region at all. So any point from this line has an x and a y coordinate that, if plugged into this formula, will give me an output of 8. But there are no points in my green region that are touching that line. That means there are no points in the green region that could give me an output of 8. So I can get certain z values out, like all of the points on the first line we drew gave me z values of 2. All of the points on the second line we drew gave me outputs of 4. This line corresponds to points that would give me an output of 6. And anything where that line intersects the region is a point that can produce that output. But there are no points in the region that can produce an output of 8. So what's the biggest value we could get out of this? Well, it's definitely something less than 8. In order to decide what that value is, let's imagine another one of these lines. It'll be parallel to the lines we've already drawn, but it will be the last line we can draw this way that actually touches the green region. So we can see from this figure that it's going to touch at just this one corner. different functions with different coefficients here, like if I were to take z equals 4x plus y, those would have given us a different set of lines to draw. Instead of x plus y equals a number, we'd end up with 4x plus y equals a number. So those lines would have been different, but again, they would have all been parallel lines, and the one with the maximum output value would have touched at a corner. So this is the idea for linear programming. In order to figure out the maximum value, all we have to do is recognize that it's going to occur at some corner of our feasible region. So in order to find the maximum value, all we have to do is figure out what the coordinates for all of our corners are and plug those coordinates into the function to figure out which one produces the greatest output. So in this picture we can see where the point is, but if we didn't go through the trouble of graphing all these lines, we wouldn't know which corner to use. But our process would be the same. We'd find the values of the corners, all of the corners, plug them into our objective function, and figure out which corner produces the output that's largest. This is a linear programming question. Everything in this problem is linear. The inequalities are all linear, and the function we're trying to find a maximum value of is linear. So for example, there are no exponents, nothing is squared. So we're only going to consider points that satisfy some constraints, some conditions described by inequalities. For example, a problem like the one we see here in blue, where we might be asked to find the maximum value of some function subject to these constraints. The function we're trying to maximize or minimize, depending on the application, is called an objective function. And the points we're allowed to plug in, the points that satisfy all of the inequalities, make up what's called the feasible region. Our general approach for solving these problems using what's called the graphical method is to first graph the feasible region, the set of points that satisfy all the inequalities. And we've already seen how to do that. Then we want to find all the corners of the region we graphed and determine the coordinates of those corners. We'll plug each corner's coordinates into the objective function, and whichever z value we get out is largest, that's the maximum value. Whatever z value we get out is least, that's the minimum value. Now, this approach assumes that the region is bounded, meaning it doesn't go off infinitely far in any direction. So, for example, you ought to be able to draw a circle that completely surrounds your region. That's what it means for a region to be bounded. We'll see some examples at the end of this chapter, or at the end of this section, where the region is not bounded, and so that we can see how that affects the thought process for a linear programming problem.